Ever wondered how a car knows it's getting too close? In this project, you'll build that idea yourself. An ESP32 parking assistant that measures distance with sound, then signals safe, caution, or danger using lights and beeps. Before we build it, let's connect what you already know. You learned the robot pattern: sense, think, and act. You used the ESP32 as the controller, then practiced with LEDs, buzzers, light, and weather sensors. Now we'll combine those ideas with distance sensing, so the system can react in real time, like a smart car. Here's the basic job. The system has to notice distance, make a quick decision, and warn clearly. The ultrasonic sensor measures space, the ESP32 chooses the alert level, and the LEDs plus buzzer turn that decision into immediate feedback. In a real parking assist system, the sensor does not drive for you. It gives useful feedback before you hit something. Far away means calm or slow beeps. Closer means faster beeps. Very close means stop now. Our project uses the same idea: measure distance, decide how safe it is, then warn or react. The whole system follows a simple chain: sense, decide, respond. The ultrasonic sensor is the input. It sends out sound pulses and measures how long the echo takes to return. The ESP32 is the decision maker. It converts that timing into distance and compares it with safety limits. The outputs are the LEDs and buzzer: green for safe, yellow for caution, and red for warning. As the object gets closer, the buzzer can beep faster, giving both visual and sound feedback. Ultrasonic distance sensing works a lot like hearing an echo in a canyon. The sensor sends out a very high-pitched sound pulse, too high for humans to hear. That pulse travels through the air, hits an object, and bounces back. The ESP32 measures how long the echo takes to return. A quick echo means the object is close. A slower echo means it is farther away. So the key measurement is not sound volume, it is time. The sensor does not measure distance directly. It measures how long the sound pulse takes to travel out, hit the object, and return as an echo. Sound travels at about 0.0343 centimeters per microsecond, so multiplying echo time by 0.0343 gives the total path traveled. But that path includes the trip out and the trip back. The real one-way distance is half of that. For a 1000 microsecond echo, the calculation is 1000 times 0.0343 divided by 2, which is about 17 centimeters. For wiring, think of the ESP32 as the controller, and each part as either sending information in or receiving commands out. The ultrasonic trigger pin connects to a digital output because the ESP32 starts each distance measurement. The echo pin connects to an input because the sensor sends the timing signal back. Since ESP32 pins use 3.3 volt logic, protect the echo line if the sensor outputs 5 volts. Each LED needs its own resistor to limit current. The buzzer also connects to a digital output, so code can switch the warning sound on and off. To read the ultrasonic sensor, the ESP32 follows a short sequence. First, configure the trigger pin as an output and the echo pin as an input. Then send a very brief high pulse on the trigger pin. That tells the sensor to emit an ultrasonic burst. Next, measure how long the echo pin stays high, usually with a timing function like pulse in. That time represents the round trip of the sound wave. Finally, convert the time to distance using the speed of sound and print the result. A single distance reading becomes more useful when we turn it into zones. If the object is far away, the system treats it as safe. Green light, no sound. In the warning range, the yellow light turns on and the buzzer beeps slowly, giving the driver time to react. When the object is very close, the red light and fast beeping signal danger. The exact cutoff values are not fixed. Choose thresholds that fit your sensor, vehicle, and practice space. Now the ESP32 turns distance into decisions. It checks the most urgent condition first. If the object is closer than 20 centimeters, trigger the red LED and buzzer. If not, it checks the warning range under 50 centimeters and turns on yellow. Anything farther falls through to the safe case, green. Because these branches use if, and else, only one alert runs at a time. Before setting the new output, clear the old LEDs and buzzer. Then test by moving an object in and out. Sound feedback gives the user distance information without requiring them to watch the LEDs. The key is to map urgency to timing. When the object is far away, the buzzer can stay silent, or use a short beep with a long pause, such as 100 milliseconds on and 800 milliseconds off. As the object approaches, shorten the pause. In the danger zone, keep the beep short, but repeat it quickly, maybe every 150 milliseconds. Make the change gradual, clear, and predictable, so it warns the user without becoming irritating. If the sensor gives strange distances, don't assume the code is broken. Start by printing values to the serial monitor and looking for patterns. A single bad number may be noise, but repeated zeros, huge distances, or sudden jumps usually point to something specific. Check wiring and power, then test with a flat, solid object at known distances. Try different angles and materials because soft or tilted surfaces can weaken echoes. Debugging sensors is about collecting evidence, then deciding whether the problem is hardware, environment, or code. To make your parking assistant more reliable, treat each update as a decision, not just one raw number. Take several ultrasonic readings close together, then ignore values that cannot be real, like negatives or huge distances. Average the remaining readings before updating the buzzer or LEDs. Add a short delay so the sensor has time to settle and the output does not flicker. Finally, test with known distances, such as 10, 20, and 30 centimeters, and compare the expected results with what your system reports. You've now connected sensing, logic, and feedback into one working system. The ultrasonic sensor measures distance with sound echoes. The ESP32 makes decisions from that data. LEDs and a buzzer turn those decisions into clear alerts. These same skills carry forward into servo smart gates, motors, Bluetooth robot cars, and obstacle-avoiding robots.